Now we come to the third category, specification driven splits. These are the trickiest because the complexity is inherent in the business domain. You can't make it go away, but you can organize it much better. When you're dealing with complex state transitions that have many rules, finite state machines provide an incredibly powerful solution. Instead of scattering state logic throughout different methods, you make the states explicit and let each state handle its own transition. Let me show you how this works with an order processing system. Here's what the scattered approach looks like. In process payment, we check if the order status is pending and payment is not null, then we can set it to paid. But if it's pending and the payment is null, we throw an exception. If it's already paid, we throw a different exception. In ship order, if the status is paid and there's a shipping address, we can set it to shipped. If it's not paid, we can't ship it. This approach scatters the state transition logic across multiple methods. Each method has to know about the current state and what transitions are valid. It's error prone and hard to reason about. But watch what happens when we make the state machine explicit. We create an order state enum where each state knows its transition rules. The pending state's process payment method checks if payment information exists. If not, it throws an exception. If payment exists, it returns paid state. Its ship method always throws an exception because you can't ship unpaid orders. The paid states process method throws an exception because the order is already paid. Its ship method checks if there is a shipping address and if so returns shipped state. The ship state throws exceptions for both operations because shipped orders can't be modified. Now, the state transition logic is centralized and explicit. Each state knows exactly what transition it allows and what operations are invalid. The business rules are encoded directly in the state machine. Your processor becomes a simple state machine driver. Process payment asks the current state to process payment and updates to the new state. Ship order asks the current state to ship and updates to the new state. This approach makes your business rules explicit and centralizes state transition logic. You can visualize the state machine, validate it against business requirements, and ensure you haven't missed any edge cases. Now, another powerful technique for specification driven splits is design by contract. When you have complex business rules that can be expressed as preconditions and postconditions, you can separate validation from business logic entirely. Here's a typical money transfer method with validation scattered throughout. We check if there are sufficient funds, if the amount is positive, if accounts are blocked, if it's the same account. Then we do the actual transfer. Finally, we verify the balances are correct. The validation logic is mixed with the business logic, making both harder to understand and test. But watch what happens when we separate concerns using contracts. Our new transfer methods start by calling transfer contract dot require valid transfer with all the parameters. This concentrates all the preconditions in one place. Then we capture the original balances, do the clean business logic, just debit one account and credit the other. And finally, we can call ensure transfer complete to verify our post condition. The transfer contract class contains all the validation logic. Require valid transfer checks all the preconditions. Sufficient funds, positive amount, unblocked accounts, different accounts. Ensure transfer completed verifies the post conditions that the balances changed correctly. Now the business logic is crystal clear. You can see exactly what the method does. It debits one account and credits another.